Alright, so we're starting our nice little calculus video series with differentiating inverse trig functions. This is uh, section 5-6 in your textbook. And I wanted to start off just by showing you the derivatives of all the inverse trig functions, and then we're going to talk a little bit about where they came from. So I've written them in this manner right here, so that you can see that arcsine is also equal to sine inverse. A lot of times they're written in one way or the other. Some textbooks I look at use arc and some use inverse. So I wanted to write them as both ways, and I generally will a lot of times switch back and forth so that you can remember that they're the same thing. One thing I wanted to point out to you is if you see there, you would the forms are really strange. Like, I would never think that the derivative of sine inverse would have no other trig functions in it. But we're actually going to show, we're going to prove today why sine inverse x, the derivative of that, is 1 over root 1 minus x squared. So you might be able to see it a little better. I want to point out to you about cosine, cotangent, and cosecant. Generally, I would only try to memorize these three right here because they're kind of opposites, you know, sine and cosine, tangent, cotangent, secant, cosecant. It's just the negative of the other. So, and also think about how derivatives work with sine and cosine in the negative. So a lot of times you'll only see them written with sine inverse, tangent inverse, and secant inverse. All right, so let's take a look at why the derivative of sine inverse is 1 over 1 minus x squared. All right, so here's our proof. This is going to be fun. I love to prove things. All right, so we want to show that sine inverse of x prime is equal to 1 over the square root of 1 minus x squared. So we're going to start with a function. We're going to let y equal sine inverse x. Now, we don't know anything about the derivative of sine inverse of x, but we know a lot about the derivative of sine. So I'm going to go ahead and I'm going to rewrite this as sine y is equal to x. I want to point out here, if you remember your rules about sine inverse, that it's only defined between negative pi over 2 and pi over 2 for x. So just so you remember for later, we're going to need that in a little bit. So now I have a function with both a y and an x. So I think that I can take and I can differentiate this using implicit differentiation. So I know the derivative of sine is cosine, and then I'm going to multiply by the derivative of the inside, that's dy dx. And then I know the derivative of x, I've taken the derivative with respect to x, so that's just going to be 1. So now I want to solve for dy dx. That's what I'm trying to find here. So I get that dy dx is equal to 1 over cosine y. Now, I really need to write this in terms of something besides cosine y. And I need to somehow write it in terms of x. So I think back to my identities, and I need an identity that involves only sine and cosine. And that is my Pythagorean identity. So let's kind of make a box over here. And that's sine squared x plus cosine squared x is equal to 1. So I can solve this for cosine x, and I end up with cosine x is equal to plus minus the square root of 1 minus sine squared x. Now, I would really like to be able to use this, but this plus minus in front of it kind of poses a problem. But then I look at where my x is defined for sine inverse. And it's only defined between negative pi over 2 and pi over 2. And lucky for us, between negative pi over 2 and pi over 2, cosine is strictly positive. So we can kind of take and erase the negative sign underneath it, and we only need to use the positive form. So I'm going to rewrite this is going to be the square root of 1 minus sine squared. And I used x over here because our original identity contained x, but this is y. So this is just sine squared y. And then if you look at the top, sine squared y, or sine y, is equal to x. So that's where the x comes in. And now I've got dy dx is equal to 1 over the square root of 1 minus x squared. Beautiful, isn't it? How neat is that? And you can use really similar proofs to show the other 5. Um, all you'd have to do is use your Pythagorean identities in whichever way you could to try to substitute in. And I think that you have a homework question, fun, where you get to prove all these for me. I thought it would be a good practice for you. All right, so here is the form that you're going to use when using the chain rule. Oh, we don't need that problem yet. So I don't tend to write out my original integrals because it makes them really messy and it makes it hard to see what the actual, or sorry, not integrals, derivative, what the actual derivative is. But if we're using the chain rule, I'll show you what one looks like and then you can just apply it to the rest. It's going to be sine inverse of some function u of x, all prime. It's going to be, let's see, how it works is, the derivative is 1 over the square root of 1 minus x squared. So it's just going to be 1 over the square root of 1 minus u of x all squared. And then, of course, because of the chain rule, I have to multiply by u prime of x. And then now I really want to write it like this, so I don't forget that I can just go ahead and write this in the numerator. U of x all squared, right? Yeah. And then it pretty much works out that all you're going to do is take and put the derivative of what you're taking the inverse trig function of, what's here, that's going to go as a derivative on the top. Because if you go back and look at all those inverse trig functions, they're all just fractions. Generally, 1 is the numerator. All right, so let's do some practice. So I thought, we'd start with simple and then we'd go on. All right, so here's a pretty simple one. G of x is equal to arc sine of 3x all over x. Okay, so I think that I'm going to write this so I don't have to mess with my quotient rule as arc sine of 3x times x to the negative 1. And then I can write it as a product rule, and I don't think it'll be quite as messy. If you want to use your quotient rule, then that's really up to you. You can try it, and we'll see if we get the same answer. All right, so my derivative is going to be the derivative of the first. So if you go back to the formula that we had before, it was pretty neat, and I can just take the derivative of my u. So here's my u is equal to 3x. And that's pretty thick, but that's okay. And so the derivative of that is 3, and it's going to go in the numerator. And then I'm going to divide that by the square root of 1 minus u of x, which is 3x all squared. And then I'm going to multiply this, because I did the derivative of the first times the second, so that's just going to be x to the negative 1 plus arc sine 3x times the derivative of the second. And I don't really think I need to show you what the derivative of x to the negative 1 is. It's negative 1 over x squared. So I'm just going to clean it up a little bit. I'm not going to get a common denominator. I think that's just a little too complicated. I will just take these two fractions and combine them together. So I get g, or I'll take the two fractions and combine them separately. So I get g prime of x is equal to 3 over, the x to the negative 1 is just 1 over x. So I'm going to put an x down here. And then this will become the square root of 1 minus 9x squared. I just distribute the power. Plus, or let's actually do minus because there's that negative sign there. Minus the arc sine of 3x divided by x squared. So I had a little practice using the product rule, and I got some practice with arc sine, so that's good practice. So we use this form a lot whenever we are working with integrating, I guess, the forms to our derivatives of inverse trig functions, going backwards from what we're doing now. So I thought this would be a good example to practice with. It's fairly simple. This is an a in the bottom here. So we want to go and look. Our derivative for arctangent is 1 over 1 plus x squared. We're going to have to, because the derivative of what we're taking the arctangent of is not 1, we're going to have to use it kind of our chain rule. So if I let u equal x over a, then my derivative is 1 over a. So this is going to be what goes in the numerator. So when I take my derivative, I have the derivative of u in the numerator, that's the chain rule part, and then I'm going to have 1 plus what I'm taking the inverse tangent of, all squared. And then kind of the neat thing about this is, let's rewrite it. Ooh, that's super big now. Alright, so what we're going to do is we are going to square both of these things. And then I can actually factor an a squared out of both of those. And if I factor a 1 over a squared out, then what I end up with is I end up, remembering when you factor out, once you redistribute, it has to look exactly like it was before. So if I want to take out a 1 over a squared, then I'm going to have an a squared here plus an x squared there. Now I have to put in the numerator, don't forget that. So let's see if I can pull this down. So this just becomes 1 over a all over that. And now one of these 1 over a's will cancel, so I won't have 1 in the numerator anymore, and then I won't have that squared anymore. And then I can take this, kind of pull it out as a constant, and if I multiply by the reciprocal of that, because I have a fraction in my denominator, it ends up putting an a in the numerator for me. And what I end up with is a all over a squared plus x squared. And that's my derivative. It's kind of neat how the algebra works out. You might want to play around with it. If you have any questions about how I ended up with it, come see me. Alright, so I picked a problem that was a little tricky, especially the algebra at the end, but I wanted to do it for you so you could see one of the harder ones. The problem looks like this. And I think one of the reasons they wrote the problem like this is because they wanted you to figure out the tricky algebra to try to combine it all as one fraction. So we have y is equal to 8 times the arc sine of x over 4 minus x times the square root of 16 minus x squared, all divided by 2. Fine, isn't that so fun? Okay, so let's try this. I'm just going to do, you have one thing subtracted from the other, so I can really just tackle both of them separately. So if you remember your derivative for arc sine, you're going to do the derivative of your u, of what's inside on the top. The derivative of x over 4 is just 1/4. I also have this 8, and the 8 is just, because it's a constant out front, just going to end up getting stuck in the numerator right there. In the bottom, it goes the square root of 1 minus x squared. But I don't just have an x, I have an x over 4. So this will be 1 minus x over 4 all squared. Alright, now I've got to deal with the derivative of the other one. So I'm just going to pull the 1/2 out front, and then I'm going to do the product rule. So the derivative of the first, which would be the x, is 1 times the second, so that's the square root of 16 minus x squared, plus the first times the derivative of the second. Kind of running out of room here. And the derivative of the second is going to be 1/2 16 minus x squared to the 1/2. Let's see if I can shift any of this over. Oh wow, it's all separate. How fun. There we go. And then, actually, the first time I worked this, I got it wrong. So don't forget, when I'm taking the derivative of 16 minus x squared, the square root of all that, I have to use the chain rule on that also. So I'm also going to have to multiply by 2x because that's the derivative of the inside. Alright, I don't want to really spend a lot of time with you all cleaning this all up. So I thought I'd play a little game, and we'll see how this goes. So I'm offering a prize to anyone who can algebraically show me that what I have for the derivative right here is equal to this. It's equal to x squared divided by the square root of 16 minus x squared. And you have to use algebra. You're going to have to get a common denominator for all of them and combine them all as one fraction. It's a pretty neat little algebraic mess that we've got on our hands. And I could do it. I did it all and I figured it out. So please make sure that you include all your steps. If you'll turn into me, then I will have a prize for you. And won't that be fun? But okay, honestly, on an exam, if I gave you a problem like this, I would expect for it to be in a simpler form than the one that I've provided you on this line. I would expect that you would clean up this area over here and, do things like making this x squared over 16 and that making that 2 on the top. And you don't want to leave it in this form. That just looks too messy. So I have one more derivative for you. It's an application problem. I thought it was a neat little problem. So I've got it over here on the next page. It's what you saw earlier. So this is angular rate of change. So we have a free fall experiment. Oh, we don't need this figure for 92. We just need 91. So we have a free fall experiment, and we have an object that's dropped from the ground at 46 feet. The position function, just in general, you would know this if you've taken physics, for an object in free fall is just negative 16t squared plus your initial height. So our initial height is 256 feet. So part A tells us, find the position function giving the height of the object at time t, assuming the object is released at a time t equals 0. At what time will the object reach ground level? So we want First, for our function, we want to plug in our initial height. This formula up here only works if your initial time is 0. So our initial height is 256, so that's what we get there. And then it wants to know at what time will it hit the ground. So all we really have to do, when it hits the ground, it's going to have a height of 0. And so if we solve this, we only want the positive when we take the square root, and we get t equal 4 seconds. All right, so the next one is the tricky part. So they tell us, find the rate of change of the angle of elevation of the camera when t is equal to 1 and t is equal to 2. So these problems are always kind of tricky, and so how I generally approach them is I ask myself, okay, what are we wanting to find? We want the rate of change of the angle. So we really want d theta dt. And if I'm going to have anything to do with an angle, I'm going to have to use a trig function. So I look and I think through my trig functions, and I look and see the ones that involve the information that I know. I know that it depends on how you look at it. My opposite is 256 and my adjacent is 500. So opposite and adjacent makes me think I'm going to use tangent. So I have the derivative of tangent is going to be my height, and height is going to change depending on the time. So we're just going to write it as height of time, in terms of time, divided by, the 500 is not going to change. So that's going to be a constant. So I have h of t actually. I wrote it down up here, right? So I can just plug that into my formula for tangent. Actually, I don't want to write it like this. I'm so sorry. This is not. There we go. D theta dt. We're going to get to that later. This is tangent theta. Oh, I don't want red. All right, so I'm going to start off by plugging in the formula I have for h of t. All right, let's see if I can go back to where I was. So we're plugging in h of t. So this is negative 16t squared plus 256 all over 500. Okay, so, and this is equal to tangent theta. So since I want d theta dt, it would make a lot of sense for me to take this equation and solve it for theta. So I'm going to take theta, and I'm going to make it equal tangent inverse. Now, this is where the tangent inverse comes in, huh? Negative 16t squared plus 256 over 500. Alright, now I want to take the derivative, and it seems like it'll be pretty nasty. The only good thing is, the problem asked me up here, if you remember, let's go back up and look at it. It wants me to find the rate of change of the angle when t is 1 and t is 2. So I don't really have to clean it all up and write a nice fancy formula for d theta dt. I just need to find out d theta dt of 1 and d theta dt of 2. So I'm going to clean it up as much as I can, but I don't have to go all the way with it. One of the first things I actually want to do is I see that I can take a 16 out of both of those on the top, and so I can write it as negative 16 over 500 times t squared minus 16. And I think that'll make it's a little simpler now. So if you remember how this works, what's going to happen is I'm going to take the derivative of the inside and put it in my numerator. So I just have this constant on the front. I have the negative 16 over 500. And then this is just going to be 2t because that derivative of the constant is going to be 0. And then I'm going to divide this by, so the formula says 1 plus x squared, or 1 plus u squared. So this is going to be 1 plus this whole thing squared. So it looks pretty nasty, but I can leave it this way. Alright, I need to write this, because that is my derivative. So now I want to find d theta dt when t is 1. I'm going to zoom this out just a little bit. Let's talk about what we got for just a second. So we wanted to find the rate of change of theta with respect to time. So if we wanted theta, we had to use tangent. We came through, we wrote our tangent in terms of height, and then the fixed base, or the fixed, what's that called? Opposite adjacent angle. And then we plugged in the formula for height that we had written, and we solved for theta because we wanted d theta dt, and then we took the derivative of that. So now we want, I think this would look a little better, yeah. Maybe I'll see just a little bit more. We want to find theta, d theta dt when t is equal to 1. So I want to find d theta dt of 1. And this is going to be, let's see, negative 16 over 500 times 2 times 1 divided by 1 plus negative 16 over 500, 1 squared minus 16 all squared. And if you plug this all in your calculator all nice and neat, you get about 0.052 radians per second. And they also ask for the rate of change of theta with respect to time when t is 2. So let's try that one. So it's going to be the same thing. And I'm going to cheat, because you can also cheat in your calculator and you can go back. That's perfect. And just plug in 2. See if this will work well for me. It's flashing funny. Alright, sweet. So I can take this. Now I'm just looking for d theta dt of 2, so all my 1's will become 2's. And I get 0.1116 radians per second. Alright, so I'm going to give you your homework assignment if you want to go ahead and get started on it. I know that you'll have another assignment due next class, but this is going to be your assignment from this section. This is what we're going to work on in class next time. If I can find it, here it is. So from section 5.6, you're going to do numbers 42 through 58 even. And then I also want you to do 62 through 66 even as well. 89, 90, and then 94, B through E. Alright, there you go.